So in this video, I just want to do a quick recap of what we did in class today and then finish off this section. You'll see another video for 6.2, hopefully no later than tomorrow night. So we talked about the fact that exponential functions and logarithmic functions are related in the fact that logarithmic functions is the inverse of an exponential function. So every time I have this log base b, what I really have is I have some base raised to a number is equal to the answer. So you want to think of this as the answer, and you want to think of this as the exponent. And of course, this is your base. So, like we said in class, because a logarithm is just an exponent, clearly that a raised to the 0 is equal to 1, because remember, this is the answer, this is the exponent, because it's an inverse. Further, a to the 1 is equal to a all day long, because this is the exponent and this is the answer. Then we talked a little bit about common logs and natural logs. So if we just see log of x, it is the common log, and what is there is its base 10. So if we see log of x or log x, then it really is the log base 10 of x. But we see it so often, we typically don't write the 10, and so all you're going to see is log x. The other thing that you're going to see is the natural log. So with the natural log, you're going to see ln. So if you see ln, then that is log base e. So log base e of x, we usually write as ln of x. Or you might see, I write it as cursive ln because my l's have a tendency to turn into ones. So I do a cursive ln of x. And this is the natural log, that is base e. So if we go back to the way that we defined generically, the log based a of 1 is equal to 0, then what we may see in the log, just the common log of 1 is equal to 0, and the natural log, ln of 1, is also equal to 0. Generically, we see in the log based a of a is equal to 1. If we are talking about the common log, you're going to see the log of 10 is equal to 1, and the ln of e is equal to 1. Some of the properties that we have with logs, because they are the inverse of our exponentials. If my base is greater than 1, then I am increasing along its domain. Now remember, when we had b to the x, when we had f of x is equal to b to the x, its domain was everything, and its range was from 0 to infinity. Because exponentials and logarithmics are related in the fact that logarithmics are the inverse of it, you will notice that the domain of my log is the range of its inverse. And the range of my log is the domain of its inverse. If b is greater than 1, this is increasing the entire time. That relates to the exponential, where b of x, where b is greater than 1. On the exponential, over here, if b is less than 1 but greater than 0, it is decreasing. And the logarithmic that relates to that looks like this. Now, if you remember that logs and exponentials are inverses of each other, if all of my exponentials go through the point 0, 1, then all of my logs must go through the point 1, 0 without transformations of graphs. And that doesn't matter if my b is greater than 1 or between 0 and 1. Our transformations will happen on our logarithmics just like they did in our previous. In our previous, we had g of x, goes all the way back to chapter 1, is equal to a, f of b, x minus c, plus d. The way we're going to see it with logarithmic functions is f of x is equal to, I'm going to have some a, the log based b. I can have big B, x minus c, plus d. So just like before, we want to do this first, and this is a reflection over x, over y, if b is less than 1, and it's a horizontal shrink stretch. The C is the second thing we need to do, and it is the left-right movement. Now remember that B and C change the domain. So what that's going to do for us is if we have B and C, that we're going to have a different domain potentially. So C will move it left and right. So because C moves it left and right, if I have a C value, that means my vertical asymptote will move left and right. Okay, going back to this, the next thing you're going to do is that, and that is going to affect your range, and it could reflect over the x-axis if that value is less than 1. It also is the vertical shrink stretch. And then the last thing you have is D. That is the last thing we typically do. So this is number 4. Let's go back over here. Change this. This should be number 3, not number 2. So this is number 3. Okay, number 4 is the last thing we do, and is our up-down movement. All right. So if I'm asked to graph this, I want to think about what the exponential may look like so that I know what the points would have been. And then I can do the transformations from there. So if I'm given the log of 3 base 3 of x, then I must have started out with 3 to the x was my original function. So I'm going to call that g of x. The only reason I'm doing that is so that I know where all my points are going to go through. Now, if I would have had the log, if I would have had 3 to the x, then I know I would have gone through this point 0, 1 without transformation. And I would have gone through this point 1, 3 without transformation. And I would have gone through this point -1, 1/3 without transformation. So my logarithmic, and I would have had here, I would have had a horizontal asymptote at y equals 0. With my logarithmic, then let's go ahead and put our, axes in here. So give me a minute. Okay, so here's our axes. And I'm going to plot the inverse of my exponential I have right here. My horizontal asymptote becomes a vertical asymptote on its inverse. So this is, I'm plotting the log, so this is x equals 0. And if my exponential would have gone through the point 0, 1, my log would go through the point 1, 0. If my exponential would have gone through 1, 3, then my log would go through 3, 1. 1, 2, 3, 1. And if my exponential would have gone through negative 1, 1/3, then it's going to go through 1/3, negative 1. So here's what my logarithmic function looks like. And that is f of x. And in a moment, we're going to do g of x. So my points of interest on my log function are 1/3, comma, negative 1, 1, comma, 0, and 3, comma, 1. So I look at what I have. I have an a value, and I have a d value. I don't have a shift left or right, nor do I have a horizontal shrink or stretch. And so all I have to deal with is the a first. And what the a does is it is a range change, and it takes all this negative 1, takes all of my y's and multiplies it by negative 1. So it is 1/3, comma, positive 1. 1, comma, 0, well, that didn't do anything. And then 3, comma, negative 1. The next thing I'm going to do is my 2. So it takes all of my range values and adds 2 to it. So 1/3, comma, and then I'm going to add 2 to the 1, so I get 3. And I have 1, comma, 2, and then I have 3, comma, negative or positive 1. So my transformed graph, I'm going to do in black, is going to go through the point 1/3 and then 3, so 1, 2, 3, so that's where that point went to. So this point, I'm going to call this A, went to A prime. This point, which is my y-intercept is B, has gone to the point 1, 2, so 1, 2. I'm going to call that B prime. And then my point, which was 3, 1, which I'm going to call C prime, has gone, well, to 3, 1. And so my C prime and my C are in the same place. So it should be C prime and C are in the same place. And so this is what my transformed graph is going to look like. This is g of x. All right, let's take a look at my next one. Ooh, yeah, actually, let's take a look at C, because C looks like it's way more interesting. So I have the natural log. The exponential function I would have started out with is e to the x. That means I would have gone through on my exponential function, would have gone through 0, 1, would have gone through the point 1, comma, e, and would have gone through the point negative 1, comma, 1 over e. So on my logarithmic graph, let's see if I can do this again. So on my logarithmic graph, put my axes in there. There we go. My logarithmic graph, ln of x, will go through the point, make this large, oh, I lost my axes. Make this a little bit larger. Didn't quite work. Let's give this a go again. So let me make this larger before I put my axes on there. So let's look at this a little bit larger, and then put my axes back on there. And my axes back on there. Okay, so I have the ln of x. That's my original function. So my original function is going to go through the point here, which is 1, comma, 0. It's also going to go through the point e, which is a little bit more than 2, almost 3, comma, 1. So it's going to go through the point e, comma, 1. And then it's going to go through the point 1 over e, negative 1. So 1 over e, negative 1. Now, if I take a look at my transformed Oh, I should probably write that in there. There is my f of x. Now, I have, for my transposed function, I have negative 2, x plus 3 minus 5. Oh, suppose I should probably put the ln in there, so just a minute. Let me put that in there. Okay. So negative 2 ln of x plus 3 minus 5. The first thing I'm going to do is this, because I don't have a b value. What this does is it moves my entire graph left 3. So if I look at my points are 1 over e comma negative 1. I have 1 comma 0, and I have e comma 1. So I'm going to take all of my x values and I'm going to subtract 3 from them. So this goes to 1 over e minus 3 comma negative 1. I have 1 minus 3, so negative 2 comma 0. And then e minus 3 comma 1. The next thing I'm going to do is this 2. So I'm going to take all my y values and I'm going to multiply all my y values by a negative 2. So I have 1 over e minus 3, and then multiplying that negative 1 times negative 2 gives me a positive 2. And then I have negative 2, and then 0 is just going to be 0. E minus 3, and I have negative 1 times a positive 1 times a negative 2 makes that a negative 2. So that's the second thing that I did. The third thing I'm going to do is I'm going to take all my y's and subtract 5 from that. So 1 over e minus 3. I'm going to take 2 and subtract 5, so that gives me negative 3. So negative 2 and negative 5. And then my last one is e minus 3, and then I'm going to subtract 5 from negative 2, which gives me negative 7. So the point A, which was right there, went to the point 1 over e minus 3. Now 1 over e is going to be, let me check, hang on a second. So 1 over e minus 3 is about negative 2.6. So 1 over e minus 3 is negative 2.6. So negative 2.6 each, and then it's going to go to negative 3. So right about here. Actually, let me do that in blue. So negative 2 and then negative 3. This is where a prime went to. Then I'm going to do negative 2, negative 5. So negative 2 and then negative 5. Let me see, 1, 2, negative 2, negative 5, which is negative 2, negative 5 is right there. This is where b prime went to. And then my next number, which is 2.72 each minus 3, negative 7, isn't on the graph. So let's just talk about where my vertical asymptote went to. So because I have a minus 3 transformation, my vertical asymptote went down here. So this is where my vertical asymptote moved to. It is x is equal to negative 3. Now my graph is going to end up looking like this because of the reflection over the x-axis and the fact that I have a vertical stretch. So that's what my g of x is going to look like. All right. If I'm asked to graph or match these functions, then I want to think about what the exponentials would be. The exponentials, and I'll just start with this top one. The exponential that I would have started out with is 10 to the x. The exponential I would have started with a natural log is e to the x, then 2 to the x, then 5 to the x, and then 25 to the x. Now, when I'm in exponentials, the larger the base, the closer I am to the y-axis. So then when I do the inverse of that, the same thing is going to hold true. The larger the base, the closer you are to the x-axis. So if I look for the one that is the closest, which is E and J must be together because they are the ones that have the largest base. Similarly, D and D of x have to go together because it's the next number in line. The next number is going to be C and H have to go together. And then E is larger than 2. So then this must go to this one. And then my last one must go to that one. Again, my exponentials, the larger the base, the quicker they increase and the closer to the y-axis they are, which means its inverse must hold true as well. The larger the base, the closer it is to the x-axis. So let's take a look at our next example here. My logs are all base 4, so that's good. And they all have a shift, or at least it looks like a shift of a left 2. Now be careful. Let's start with our easiest one, which is this one. We're going to start with this one, and we know that this moves everything left 2. So it takes my graph, which should have gone through the point 1, 0, and moves it left 2. So that means that A and H are together. My next one I'm going to look at, the next easiest one, is the fact that I have a negative in front of the log. That tells me I have a reflection, and it's going to be moved over to. So that's that one. So C and G of H, or G of X, come together. The last one I have to look at, and that's the one I said to be careful about, is this. It is not in the right form. The form that we want is f of x is equal to a log base b of b x minus c plus d. The importance is that the coefficient on the x is 1. And if the coefficient on x is 1, then we need to factor that out, and that is our b value. So to put this in the correct form, this is going to be equal to the log base 4 of, I'm going to factor out a negative 1. Then I have a positive 1 coefficient, and then minus 2. So what really happens with that graph is that I am not moving left 2, I'm actually moving right 2. And when I'm moving right 2, I have this reflection across the y. So even if I didn't have it by process of elimination, I could have reasoned through that, and so that graph, which is b, goes with f of x. So now let's just kind of do a check between exponentials and logarithmics. Notice that this is increasing the entire time if a is greater than 1, and that means that my log, which is the inverse, is also increasing. My horizontal asymptote becomes a vertical asymptote on my inverse. My domain is all real numbers, which becomes the range of my inverse. The range of 0 excuse me, 0 into infinity becomes the domain. They're both continuous, they're both 1 to 1. They're both increasing. The asymptotes switch. There is no x-intercept on my original exponential, which means there's no y-intercept on my log. And I do have a y-intercept on my exponential, which means I have an x-intercept on my log. if I'm asked to convert these into exponential and logarithmic and back again, I use this definition. Remember, this is the base, this is the exponent, and this is the answer. So that means I have 4 raised to the t is equal to 7, and that's what it looks like as an exponential. Let's do this again. This is my base, this is my exponent, and this is my answer. So it is 5 raised to the x is equal to 7. Let's do this again. My base is missing, so it's a log, so it's the common log, so it's base 10. This is the exponent, and this is the answer. So it is 10 raised to the 5th is equal to A. Last one. This is my base, and it's a natural log, so it is E. This is my exponent, and this is my answer. So this is E raised to the y is equal to 6. Now that we've gone from log to exponential, let's go from exponential to log. This is my base, this is my exponent, and this is my answer. So it becomes the log base m of n is equal to -7. This is my base, this is my exponent, this is my answer. So log base 7/5 of n is equal to m. Couple more. This is my base, this is my exponent, this is my answer. So this is the common log, so it's just log of b is equal to a. And I can put 10 there, but I don't have to because it's the common log. Same thing for the next one. Oh, wait, this is where wanting us to go back into exponential. Okay, cool. My base is 10. My answer is 1,000. My exponent is 3. So 10 raised to the 3 is equal to 1,000. Last one. My base is E, my answer is Y, my exponent, or my answer is X, my exponent is Y. So this is E raised to the Y is equal to X. Whew, okay. So on these, they're asking us to evaluate them without a calculator. So we ask ourselves, what do we raise 3 to? So 3 raised to what is equal to our answer, which is 1/27. Well, the answer is -3. 3 raised to the -3 makes us 1/3 squared, which is 1/27. So my answer is -3. I ask myself, how do I go from 2 and get an answer of 1/8? So just looking at this part of it, so 2 raised to the what is equal to 1/8. And that also is -3. So this is equal to -3 plus 4, which is just 1. So when you're out with your friends this weekend and they ask you how many sodas you would like to drink, you're going to say the log base 2 of 1/8 plus 4 sodas, please. You will be the life of the party. If we take a look at our next example, this is my base. This is my answer. I'm going to ignore the 6 because I don't need the 6. 6 is just going to be a multiplier. So I ask myself, how do I get from 8 to 4? Remember, 4 is my answer. Well, this one's going to take a little bit more work than just our regular, let's just go from 8 to 4. One of the ways that we can go from 8 to 4 is that we know that the square root of 8 does not give us 4. But if I have the cube root of 8, I will get 4. So that means that this is going to be equal to 6 multiplied by 1/3, because remember, the cube root of 8 can be wrote as 8 raised to the 1/3. So 6 times 1/3 is just 2. Our last example here, I am asked to evaluate the natural log of e. Well, we know that's 1 plus 2, so my answer is 3. For these examples, I just want you to plug them in your calculator just to make sure that you are comfortable with putting these into your calculator. And I'm not going to go over those in this video because it's just plugging into the calculator. If I'm asked to find the domains, I ask myself, when do I have domain restrictions? I have domain restrictions first when I have a rational function and I have a restriction in the domain because of the denominator. The second time I have a domain issue or domain restriction is when I am taking the nth root of something, like the nth root of x, and I can't have whatever's underneath the radicand be less than 0. So whatever's underneath the radicand has to be greater than or equal to 0 when n is even. Now we've picked up something new. The new thing we have picked up is if I have the log base b of x, my domain is from x has to be strictly greater than 0. So we picked up something new. On our example A here, it is none of these. Because that is none of these, my domain is everything. On our example B here, though, I see I have a log. Because I have a log, then what ends up happening here is I have x plus 3 is strictly greater than 0. That means x has to be greater than -3. And I know that's happening because this plus 3 is moving my entire graph, including my vertical asymptote, to the left 3. So my domain is from -3 to infinity on this. My next example is x squared minus 3x minus 4 has to strictly be greater than 0. So this goes back to our polynomial inequalities. That means I'm going to have to factor this. So x minus 4 multiplied by x plus 1 is greater than 0. So now I'm going to do a sign chart. X minus 4, x plus 1, and I have -1, and I have 4. My first interval is from -infinity to -1, -1 to 4, and 4 to infinity. So I'm going to choose something in the interval between -1 or -infinity and -1. So I'm going to choose -4 because I can. That gives me a negative and a negative. That tells me this region is positive. I'm going to choose something in this region. I'm going to choose 0. That gives me a negative and a positive, so that region is negative. And I'm going to choose something on the other side of 4, so I'm going to choose 10. That gives me a positive and a positive, so that region is positive. So going back here, my domain is this interval, so from negative infinity to negative 1, union with 4 to infinity, because these are the two intervals in which I have positive regions. Okay, my last example, D, because my index is 4, I have to have this entire thing, the log of x minus 2, to be larger than 0. Okay, cool. But before I even do that, I have to have this x minus 2 be larger than 0. Because the x minus 2 has to be larger than 0, then x has to be larger than 2. What that's telling me is that my graph has gone to the right 2. Okay, so at the very minimum, I get to have 2. But here's my graph, right? So if I move my graph over, so my vertical asymptote is that x is equal to 2, I have a graph that looks like this. Right here is my x-intercept. My x-intercept has moved over 2 as well, so this goes to 3, 1. I have to have my log of x minus 2 to be strictly greater than 0. That means the only part of my graph of the log is this part right here. That's the only part I get. So my domain for D, so I'll just write it over here. My domain for f, over here, f of x, domain is going to be from 3 to infinity. All right, almost done. So the reason we learn exponentials and logs is because we actually have applications for them that make sense. If we have an exposure EI index for a 35 millimeter camera, and I know all of us use our phones now, but there used to be a time in which we had 35 millimeter cameras, and some photographers still use their 35 millimeter cameras. It is EI, the exposure index, is determined by the log base 2 of f squared divided by 2, where f is the f-stop setting on the camera and t is the exposure. Suppose the f-stop setting is 8 and the desired exposure time is 2 seconds, what would it be? Well, then this would be the log base 2 of 8 over 2, which is, before you get your calculators out, this is the log base 2 of 4. So I ask myself, what do I need to raise 2 by to get 4 as the answer? And that is going to be 2. The answer is 2, because that's the exponent. All right, last one. The average student score T, so students in accounting class took a final exam, and when they took the equivalent forms of the exam at a monthly intervals thereafter, the average student ST score as a percent after T months was found to be given by this function. What does 78 represent? Well, 78 represents their initial average score when they took the final exam. If I wanted to know what their score was after 4 months, then what I'm asking you to do is find S of 4. So this is going to be 78 minus 15, the log of 4 plus 1. And we're going to get our calculators out, and this is something we can do because it's the common log, and we see that on our calculator. So 78 minus 15 times the log of 5. And my answer is, after 4 months, their score was 67%. Remember, these are your accountants. What is it after 2 years? Well, that's S of 24. So this is 78 minus 15, the log of 24 months plus 1, which is equal to, I'm going to get my calculator out, 78 minus 15, the log of 25. So after 2 years, they're going to score 57%. Now, with that said, I know this is tax season, is don't go out and fire your accountant. It just means that the final exam that they took is not always a good representation of the knowledge that they need to be out in the public sector and doing your taxes. So anyways, there it is. You'll see another video probably tomorrow night for 6.2.